Hi everyone, let's have the continuation of last class. So last class we had a normal introduction on the overview of what is pulse oximetry and what is the basic components which is being involved in a pulse oximetry device, right? Now let's have a detailed discussion of working principle and what is the property of pulse oximetry. Okay, so actually the pulse oximetry follows the three physical properties. The thing is that in pulse oximetry we have to measure what is the concentration of oxyhemoglobin and deoxyhemoglobin. Then only we can able to know what is the oxygen saturation, right? So for that we have three physical properties. Based on that only we will have this measurement in terms of oxygen saturation. So the what is a property in the sense these all three properties follows one law, that is Beer-Lambert's law. So the pulse oximetry follows the Beer-Lambert's law. This law states that amount of light absorbed by the substance which is directly proportional to the path length of the light through the medium and the concentration of the absorbing substance in the sample, right? So this is the Beer-Lambert's law. So let's see the first property one. So the property one is that the amount of light absorbed by the substance is directly proportional to the concentration of light absorbing substance present in the medium. It means that you are passing the light, okay, from the light source the light is passing all the way through the finger. That means it passing atrial blood and venous blood and then reach the photodetectors. Okay, so it is the pulse oximetry component like clip like device. Just you will be placed over the finger, and the top of the clip you will be having the light source and bottom of the clip you will be having the photodetector. So the light source will start to pass the light through this finger, and then remaining light, okay, based on the absorption the remaining left out light will be absorbed by the photodetector. So this is how the function the mechanism will go on. The thing is that when it goes all the way to the photodetector, there will be some absorption will be take place based on the concentration of molecule present in the blood. Okay, so you have two molecule, that is we are focusing here in the what we are focusing here in the sense oxyhemoglobin and deoxyhemoglobin. Based on the light wavelength, both will have a different absorptions values. Okay, so what they are telling in the sense in the property one, the amount of light absorbed by the substance is directly proportional to the concentration of the particular molecule present in the substance. So if you have more absorptions, it means that the concentration of the oxyhemoglobin and deoxyhemoglobin is also more in that sample, in that blood. So this is the property one. Second property is the amount of light absorbed is directly proportional to the length of the light path. Okay, so if you increasing the light path length, obviously the absorption rate will be high. The blood have more enough time to absorb the more light, so the amount of light absorbed which is directly linked with the length of the light path. So this is the property 2. And third property is that as I said before, the oxyhemoglobin and hemoglobin have a different optical characteristics, unique optical characteristics. So the oxyhemoglobin absorbs the more infrared light compared to the deoxyhemoglobin, and also deoxyhemoglobin absorbs more red light compared to the infrared light. This is the reason in pulse oximetry you can see two light source. One is infrared light, another one is red light. Okay, so these are the three important properties through which all the functionality of pulse oximetry is follows. And from this we are calculating what is the oxygen saturation. Okay, so this is the graph. If you see here, in the x-axis is the wavelength and y-axis is the absorbance. Okay, so and you can see the two curves, one is in blue color, another one is pink color. The blue color one is it's nothing but this is the curve for venous blood, and pink color one is nothing but this is the curve for atrial blood. The reason is that you have the in whole setup of procedure, you will be placing the clip like pulse oximetry over the finger. So inside the finger you have both atrial blood and the venous blood. You are not focusing only the atrial blood. That is the reason you are having the two curve. One is atrial, another one is venous. Okay, so the atrial, if you see, if you do the plot, okay, there is a two wavelength you are focusing here. One is red light, that is 650 nanometer, another one is 950 nanometer, that is infrared light. So when you make the point, okay, which is point at that respective wavelength, and if you are correlating this point towards the absorbance, in the sense you can easily get what is the absorbance of oxyhemoglobin at particular wavelength, what is the absorbance of deoxyhemoglobin at the particular wavelength for both venous blood and the atrial blood. Okay, so if you see the blue curve, the deoxyhemoglobin is very high and compared to the oxyhemoglobin absorbance value, and similarly if you see the pink color, there you can see the deoxyhemoglobin absorbance value is very low compared to the oxyhemoglobin. That is the case, right? So obviously in venous blood deoxyhemoglobin will be more compared to oxyhemoglobin, and then in atrial blood deoxyhemoglobin value will be less compared to the oxyhemoglobin. So based on that concentration only, your absorbance value also will have a same value, right? So if you have more means absorbance will also more. If it is less means the absorbance value also less. So this how we will calculate the what is the respective oxy and deoxyhemoglobin for atrial and venous blood with the help of this graph. And if you take all these values, and if you have one set formula, when you're substituting those value in that formula, you come to know what is the ratio of the absorbance. When you want to measure the SpO2 value, that is the oxygen concentration in terms of percentage, we have to calculate what is the ratio of the absorbance. For that measurement, we have one formula, that is R is equal to AC 960 divided by DC 960 and whole divided by AC 660 nanometer divided by DC 660 nanometer. So those values, the 660, 960 is nothing but you know already, that is the wavelength, light wavelength. And AC, DC here they are correlating with the flow, pulsatile flow. The AC means for in simple terms, AC means alternating current, DC means direct current. So if you are correlating with biological terms, in the sense AC is nothing but is a pulsatile flow and DC is a non-pulsatile flow. It is related to atrial blood and venous blood. So pulsatile means they are mentioning the venous atrial blood, and non-pulsatile means they are mentioning the venous blood. So if you are taking the absorbance in both case, absorbance of oxy, that is infrared and red light for venous blood, and absorbance at infrared and red light at atrial blood. So if you take all these four values of absorbance and from this graph, that is absorbance wavelength graph, and if you put the values in this formula, that is ratio of the absorbance formula, R is equal to AC divided by DC, that formula, you will get to know what is the ratio of the absorbance. Once you get to know what is the ratio of the absorbance, you have to put this R value in another formula, that is a formula to measure what is the SpO2, that in terms of 100%. That formula is SpO2 is equal to 100 into 1 minus R. So already you know what is the R value. If you substitute that R value in that formula of SpO2, then you come to know what is the SpO2. So this how the device is working to give value of what is the oxygen saturation, right? I think you now get to know how the oxygen concentration is being observed by using the law, that is Beer-Lambert's law, by following three properties. And with the help of this graph, we will have absorbance value for all four all two oxy, deoxy at venous blood and venous at atrial blood. And when you substituting those values into different set of formulas, finally we will have what is the SpO2 value, right? So this is all about pulse oximetry working mechanism and the formula which is being used to get the values. Thank you.